Welcome to 5.3, solving trigonometric equations. This is generally the split of our semester, so we're beginning semester 2 work perhaps. That might change from year to year, but that's the plan. It's kind of nice to be away for a couple of weeks and then come back and review the trigonometric properties that we've talked about. And in this case, it's going to be in conjunction with solving equations with those. So let's get started here. In exercise 11 through 16, find all solutions of the equation in the interval. This is going to be a biggie for us, whether we're degrees or radians, or whether we want all the solutions, all possible solutions, or just one revolution's worth. We have to read the end of the instructions really carefully here. In this case, we're in degrees, but only 0 to 360. Now, if I've got sine or cosine or secant or cosecant, or for that matter, tangent or cotangent, I've got equals 0 or equals 1 or equals -1. Probably the best way to do this is if we know what the graph of cosine looks like. The graph of cosine from 0 to 360 degrees looks like this. At 180 degrees is when it hits -1. The answer to this is 180 degrees. Now we can do this. We can say, well, cosine is the ratio x on r. When is x on r -1 to 1? Well, that happens when x is -1 on a radius 1, but there we are, 180 degrees, and that's the only time it happens. So x equals 180 degrees. Now it's worth noting that it would be 180 degrees negative as well, or 180 degrees plus another 360, or minus 360. There's an infinite number of times cosine is -1. Okay, now this is not a quadrantal situation. Quadrantals are like when cosine, sine are 0, 1, -1, etc. as we move along. The graph of the function is really helpful if we know what the graph looks like. So in this case, I'm just going to treat this as when is x on r in ratio square root of 3 to 2. That's square root of 3, 1, 2 right triangle. X is alongside here, and x is positive. So x is long square root of 3 to 2 to 1. Also, cosine is positive in the fourth quadrant. All students take calculus. Cosine's positive down here because x is positive square root of 3. So people will miss this even though they know this is 30 degrees. They will say 30 degrees and -30 degrees, but we're only allowed to go positive rotation, so we're 30 degrees shy of 360, 330 degrees. Got to read those instructions. That's the most likely case where you'll miss the problem even though you really understand the material. Okay, tangent of x. When is it negative square root of 3? Well, tangent is y to x in ratio of negative square root of 3 to 1. That's a square root of 3, 1, 2 right triangle where tangent is negative. Y is the long side compared to x, so we have tall triangles, but tangent's positive here and here. All students take calculus. We need to build tall triangles. Square root of 3, do that again, square root of 3 on -1, and a tall triangle, or tall upside down, negative square root of 3 to +1. I'm sorry, this is positive square root of 3. Positive square root of 3 on -1, negative square root of 3 on +1. So if this is a 60-degree angle in here, which it is, then we're 120 degrees short of 180, and we don't call this one -60. We're 60 shy of 360, 300 degrees. So I guess most important thing there, reading the directions, what are they really looking for? Okay, same material. Now we're looking for one revolution, but we're going to be in radians here. Sine y on r, -1 to 2. That's a 1 square root of 2, or square root of 3 to 30, 60, 90, where the y value is short and we're going down. Y is negative, so we're here and here. All students take calculus, signs positive, up, because that's where Y is positive, up. So short Y value, so maybe something like this, -1 and 2, -1, 2, Y to R, 30, 30. But we can only, and those are degrees, so we have to be talking in radians first, and we can only go forward. So this angle is pi on 6, so we're pi plus another 6th pi. X is 7/6 pi, and 1/6 pi short of 2 pi, or 1/6 pi short of 12/6, 11/6 pi. And this, truthfully, this is things that we did back in chapter 4. Okay. When is sine square root of 3 on 2? When y on r is square root of 3 on 2. That's a square root of 3, 1, 2 right triangle. That is tall. Sine is positive in the first two quadrants. Tall triangle, square root of 3 on 2. Oh, not very good triangles there. Square root of 3 on 2. The x is irrelevant in this case, but we have to be up. So this is a 60-degree triangle, or a pi on 3. And this is pi on 3 shy of pi, or pi on 3 shy of 3/3 pi, 2/3 pi. Okay, and we've talked about derationalizing before. Hopefully we all recognize this could come from 1 on square root of 2. That is, x is to r as 1 is to square root of 2. That's a 1, 1 square root of 2, 45, 45 right triangle, where x is positive, and x is positive to the right. 1 on square root of 2. Oops, here's a 1, x. 1 on square root of 2. Here's a 1, -1 square root of 2, but x is still positive. So this is a 45-degree, or 1/4 pi. That's pi on 4. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4 pi. Okay, let's continue. Secant is the ratio square root of 2 on 1. Secant is r on x is in ratio square root of 2 on 1. If you want to convert that to cosine of x is 1 on square root of 2, be my guest. But this again is a 45-45 where x is positive. Should sound familiar. .45's here, or pi on 4. So once again, x is pi on 4, or 7/4 pi. That's the exact same problem as number 22. Okay, when is secant plain old 2? Well, secant is plain old 2 when r to x is 2 to 1. That's a 1 square root of 3, 2 right triangle, r being the hypotenuse 2. X is 1, so x is short, and x is positive, so we're to the right. 1 square root of 3, 2. 1 negative square root of 3, 2. That is a pi on 3, 60 degrees, pi on 3. So x is pi on 3, 1/3, 2/3, 3/3, 4/3, 5/3 pi, or 1/3 short of 6/3 pi. And cosecant, negative square root of 2 on 1. That is r on y, reciprocal of sine, is in ratio negative square root of 2 on 1. But r is not negative, so you might want to think of it as -1 down here. Y is negative. That's a 1, 1 square root of 2 right triangle, 45-45, where y is negative. Right here and here, 45. So that's 1/4, 2/4, 3/4, 4/4, 5/4 pi, 6/4, 7/4 pi. And to be honest, that is all just review, but what a good time for us to be reviewing. Now we just take that to the next step. And here we have an equation to solve, and this just says solve the equation. It doesn't give us degrees or radians. It doesn't give us 0 to 360 or 0 to 2 pi. It doesn't tell us 1 revolution. So we're going to assume for this that we're going to be in radians. I believe the back of the book is. But we need all of the solutions. So we're going to treat this just like it's a variable and solve for sine of x. So this would be sine of x equals, we would subtract 1 first and then divide square root of 2, and we just turned this problem into what we were just looking at. So when is y on r in ratio -1 to square root of 2? When y is negative, that's down. This is a 1, 1 square root of 2 right triangle. And here comes the tricky part. See, sine hits negative. Here's the graph of sine. Sum of the graph of sine. Looks like this. And somewhere along the line, sine hits -1 on square root of 2. And then it hits it again. But in reality, it hits it again and hits it again. And sooner or later on down the road here, it's going to hit it again and hit it again. There's an infinite number of solutions. And that's what they're asking for, all of the solutions. So how do we name those? I'm going to go to this one first. Here's 1/4, 2/4, 3/4, 4/4, 5/4 pi. So x equals 5/4 pi, but it equals 5/4 pi and 5/4 pi plus 2 pi, plus 2 pi, plus 2 pi, or 5/4 pi minus 2 pi, minus 2 pi, minus 2 pi. And that's where we go, plus multiple revolutions, 2 pi n. Or 2n pi. See, 2 pi is a revolution. We should state that n is an integer. So if n is 4, go to 5/4 pi and then spin around the circle 4 more times. Or if n is -1, go to 5/4 pi and spin backwards 1 time. Okay, or we could go to 7/4 pi and spin multiple revolutions. So you're going to think we always put this 2 pi in, or I'll probably start using 2n pi. It just seems to sound better to me, but same thing. So you're going to probably think, well, we'll just always just add 2 pi n to our answers, and that's an option, but there's oftentimes an abbreviation for that. Okay, let's take a look at 34. We're going to solve for cotangent squared. Cotangent squared of x equals, we're going to add 1, divide 3. Then to get rid of a squared, carefully we go cotangent of x equals plus or minus square root of 1/3, which is plus or minus 1 on square root of 3. And cotangent is x to y. Okay, that's a 1 square root of 3, 2 right triangle. It's tall, and it's where tangent and cotangent are negative, second and fourth. But y is the tall, y is the big length, x is the short length. So I'm going to draw my triangles tall. Here's a square root of 3, -1. And tall, but upside down, negative square root of 3, 1. Sure enough, this is a 60-degree or a pi on 3. So to get to this angle, I can go 1/3, 2/3 pi. X is 2/3 pi. And I could put plus multiple revolutions. Go here and rotate around again, and rotate around again, or rotate backwards a few times. So I could put plus 2n pi here, but note, if I just rotate pi, I hit this answer. So rather than rotating multiple revolutions, I'm going to just rotate multiple half revolutions. And that takes care of our full answer. That's probably the way the back of the book would answer it. Now, I do want to note, it would be okay to say this. X equals negative pi on 3 plus multiple half revolutions. Could just go here and rotate. So either one of those would be fine. It still picks up the other answer when we go a half revolution around. So you don't need both of these. Either one of these would be fine for an answer. Okay, then a little more complicated problem here. Maybe I could zoom in here, give you a little bit of perspective, better view. Temptation might be to go ahead and distribute this through, but if I was solving an equation, let's see, this doesn't look too much different than x times x minus 1 equals 0. If I had that equation, is there a benefit in distributing other than showing off our algebra skills? Don't we like it in this form where we can say x equals 0, x equals 1? So I'm going to treat this problem like that. So cosine of x times quantity cosine of x minus 1 is 0 when this is 0, or when cosine of x minus 1 is 0. I like it in factored. That was actually a gift. So cosine is 0 when x on r is in ratio 0 to 1, and cosine of x equals 1 when x on r is in ratio 1 to 1. Now, again, we could get this from the graph of cosine. We could build triangles, these quadrantals, but I'm going to get this from the graph. Here's the graph of the first revolution of the graph of cosine. Looks like this. 2 pi, pi, pi on 2, 3/2 pi. So when is cosine 0? Cosine is 0 at, let's take a look here, rotationally speaking, cosine is 0 at pi on 2 and 3/2 pi. And when is cosine 1? Cosine of 1 is 0, or cosine of x is 1 when x is 0. We have 0 revolution, and not again until here. So those are our three solutions. So how could we name those? We could say, well, x equals pi on 2, right here, plus a half revolution and another half revolution and another half revolution, plus multiple half revolutions. But that didn't pick up this angle. So, or x is 0 plus multiple revolutions, multiple full revolutions, 2 pi n or 2n pi. Obviously, you don't need the 0 here. You could just have, don't need another comma there either. You could just have multiple revolutions. 0 could be implied, but that kind of makes sense to me to have that there. Okay, so that's how we handle all sorts of answers. And once again, we're going to always go back. We're going to read that really carefully because here we are back to just a 0 to 2 pi. Then they say use the table feature of a graphing calculator. We'll do that on some, but not on all. Use the table feature of a graphing calculator to check your answers, but find all solutions to the equation from just 0 to 2 pi algebraically. We're going to do it that way. Okay. If this was plain old x and this was plain old x, I'd group my x's on one side. So I've got 3 signs. I'm going to subtract this sign across and get 2 sine of x plus 1 equals 0. And I just turned problem 38 into a problem like 30, 34, 36. Solve for sine. This says when is sine of x equal subtract 1 divide 2. That's when y on r is in ratio -1 to 2. And certainly by now we should recognize that that is a 30, 60, 90, a 1 square root of 3, 2, where y is the short part and y is negative. X would be the square root of 3 side, so y is short. This triangle is short, -1. Short, -1. Good news, we only need answers from 0 to 2 pi. Bad news, we can't go backwards here even though it's convenient. This is 1/6 pi. 1, 2, 3, 4, 5, 6, 7 6 pi. 7, 8, 9, 10, 11. 1 short of 12. 11 6 pi. Common mistake answer here is negative pi on 6. It doesn't fit in our domain of answers. Okay, dangerous time right here, and I'm going to warn you and warn you and warn you, and those that listen well will be fine, and those that don't will be tempted to divide both sides by tangent. I'm telling you, if you do that, you will lose a solution, or you may lose a solution. You do not want to divide by a trig function. It's a good general rule just to say don't divide both sides of an equation by a trig function, but you cannot divide both sides by a trig function if the trig function may be 0 and tangent may be 0. So don't do it. If you're ever tempted to divide by a trig function, like we certainly would be here, group them. 3 tangent cubed of x minus tangent of x equals 0, and factor. Tangent of x times 3 tangent squared of x minus 1 equals 0. So either tangent of x equals 0, or, let's see, I'll do a little bit of the algebra here. Tangent squared of x equals add 1, divide 3. So that's y is to x equals 0. Square root of both sides, y is to x is plus or minus square root of 1 is 1 on square root of 3. So let's take a look. When is y on x 0 on 1 when y is 0? Here and there. When is y on x 1 on square root of 3? Those are 30, 60, 90s where x is long. It happens here. It happens here. It happens here. It happens here. All of those would be ratios 1 on square root of 3. Those are all 30, 60, 90 triangles, 30-degree reference angles. So let's see. I could choose to call, we're just one revolution, not multiple revolutions. So I'm just going to name all of those solutions as we go around. X could be 0. There's 1/6 pi. Let's see, 2, 6, 3, 6, 4, 6, 5, 6 pi. Pi, 6, 6, 7, 6 pi. And 1/6 pi short of 12/6 pi. 11/6 pi. Now, I'm going to tell you right now, if you divide both sides by tangent of this, you would lose this answer and that answer. And that's going to be at least 50% off for that problem if you do everything else correctly. Do not divide both sides of an equation by a trig function, particularly if the trig function can be 0. If this was 3 secant cubed of x equals secant of x, you could divide both sides by secant. I still don't. I like the general rule better than the specific rule. See, because secant can never be 0, but sine, cosine, tangent, cotangent can be 0.